Chapter 11, Intermolecular Forces and Liquids. So this chapter includes 6 major topic areas. The first is going to be states of matter and intermolecular forces. Then we're going to talk about interactions between ions and molecules with a permanent dipole, interactions between molecules with a permanent dipole, and intermolecular forces involving non-polar molecules. A summary of van der Waals intermolecular forces will then follow, and finally we'll talk a little bit about the properties of liquids. So there's some questions to ponder with regards to all this. For example, why is water usually a liquid and not a gas? Why does liquid water boil at such a high temperature for such a small molecule? Why does ice float on water, and why do snowflakes have 6 sides? And why is iodine a solid whereas chlorine is a gas? And finally, why are sodium chloride crystals little cubes? All of these questions may be answered by intermolecular forces. So what we're seeing here is that water boils at a ridiculously high temperature for its mass. So methane, which has a reasonably similar mass, that's CH4, the tetrahedral molecule that we've heard so much about, has a mass of 16 grams per mole. Water's mass is 18 grams per mole, but yet there is a huge difference between their boiling points. And why is that? Well, ultimately it comes down to intermolecular forces. They're much stronger for water than they are for methane. But let's continue on and think about some of these problems. So the forces holding solids and liquids together are called intermolecular forces. Intermolecular forces are the attractions and repulsions between molecules. They are not chemical bonds. I want to emphasize this. They are not chemical bonds. They are simply physical bonds. They can be broken without changing the structure of the molecules themselves. The intermolecular forces of a substance are a function of the charge. So we've got ions versus neutral molecules. So ionic compounds, the ions attract each other very strongly. Positive attracts negative and so on. Polarity, so that is affected by molecular shape, and dipoles. So some molecules such as water have a considerable dipole moment. And then molar mass, the larger the molecule is, or the number of electrons it has, will affect the amount of electrons that are available to be used in these intermolecular interactions. It also can help to reduce sort of the repulsion between the positively charged nuclei. In very small, like say first, second row period atoms, the nucleus is actually quite close to the valence. But as you go further down the third, fourth, and fifth shells, what you see is that the nucleus gets further and further away from the valence, which is where ultimately most of the interactions occur. And so the repulsion is kind of reduced. Intermolecular forces influence chemistry in many ways. They are directly related to properties such as the melting point, boiling point, and the energy needed to convert a solid to a liquid or a liquid to a vapor. They are important in determining the solubility of gases, liquids, and solids in various solvents, and they are crucial in determining the structures of biologically important molecules such as DNA and proteins. States of matter. So here we have liquid nitrogen and have gaseous nitrogen. So when a 300 milliliter sample of liquid nitrogen evaporates, it will produce more than 200 liters of gas at 25 degrees Celsius and 1 atmosphere. In the liquid phase, the molecules of nitrogen are close together. In the gas phase, they are far apart. So here, ultimately, like a lot of this comes down to these intermolecular forces fighting against or competing with a kinetic energy. So in the case of nitrogen in the gas phase, the kinetic energy has won and it is stronger than, or has more energy than, the intermolecular forces. So the intermolecular forces are working to try and hold it together, but they have a finite strength. And if that strength is overcome considerably, we end up with a gas. If it's about equal, we end up with a liquid. And if it is strongly in favor of the intermolecular forces, then we have a solid. Typically, we get that sort of situation whenever we cool something down. Think of ice freezing in your refrigerator. So the same volume of liquid benzene, C6H6, is placed in 2 test tubes, and one tube right is cooled, freezing the liquid. The solid and liquid states have almost the same volume, showing that the molecules are packed together almost as tightly in the liquid state as they are in the solid state. So here is liquid benzene, here is solid benzene. You can see that the volumes are comparable. You couldn't really say that, at least from this, that there's a significant difference in the densities, but there's a significant difference in the way that they are packed together. The analogy here is that the solid is more like students in a classroom. Everybody's sitting in their seats, ordered, low kinetic energy. The next thing would be as the bell rings and everyone files out of the room, and people start to get closer together. They're more associated with each other, but they have higher kinetic energy. So they're free to move, but they're also quite close together. And then the last one would be the gas phase, whenever the students leave the classroom and go about their day, maybe to another class, maybe to lunch or whatever. And so at that point, they're moving randomly, they're moving in different directions, different places, much like a gas. So why is something a solid, a liquid, or a gas? Well, as I've said, it ultimately comes down to this sort of competition between the various kinetic energy versus intermolecular forces struggle. So the balance here is of kinetic energy and intermolecular forces. So kinetic energy is molecular motion, so how fast the molecule or particle is moving around. And intermolecular forces are these attractions between particles, atoms, molecules, and ions. Intramolecular versus intermolecular. So we have intramolecular forces. Those are bonds. So a chemical covalent bond or an ionic bond, those are intramolecular forces. Here we have some molecular stability. Intermolecular forces are particle attractions. They affect the bulk properties, the freezing point, the boiling point, etc. of our system. So as the intermolecular forces start to outweigh, we end up with outweigh the kinetic energy. We start to get solids. Whenever there's reasonable parity between the two, what we end up with is a liquid. And then if the kinetic energy is very high, we'll end up with a gas. So directly related to so the intermolecular forces are directly related to properties such as melting point, boiling point, and energy required to convert solids to liquids or liquids to vapors. And it's very important in determining the solubility of gases, liquids, and solids in various solvents. It's also crucial in determining the structures of biologically important molecules such as DNA and proteins. Now, this is important because it's very important to the biology that surrounds us. It's very important just to life as we know it, that these proteins interact with each other intermolecularly in the same way. So one of the great unsolved mysteries in science is, why do proteins always fold in exactly the same way? So proteins are very large molecules. They have many atoms. They have many interactions, but sort of 1 in a billion chance of something going wrong, maybe even 1 in a trillion. And that doesn't mean that every trillion events that happen, it happens once. No, it just means that every time it happens, it's got a 1 in a trillion chance of it happening. That's how rare it is that it would go wrong. And whenever it does go wrong, usually that causes some sort of an illness or like some sort of condition or disease or something along those lines. And it really affects the life that we know. Something has gone wrong, unfortunately. But like I said, it almost always goes correctly. And these are large molecules, and for them to fold in exactly the same way every time is quite odd, because usually something that large and with that sort of structure, we would assume that there would be a distribution of, I mean, of course, the correct structure would be a possibility, but usually you would have a distribution of possibilities. But that's not what happens. It basically goes into the same structure of folding the different chains together every single time. And so that's an incredibly important question that needs to be answered, and it's probably a Nobel Prize if you can do it. So here we're going to draw some representations of the following. So I'll ask you to do this, pause the video if you need to, and draw out sort of your representations of these on a piece of scratch paper or something, and then I'll go through it with you. So 5 or 10 seconds, pause if you need more time. Pause if you need more time. Okay, so let's draw the representation of the first one. So that will be a dipole moment. So usually in chemistry, we draw a dipole moment like this, with the arrow pointing towards the negative part of the molecule or pointing from the negative part. And then the part with the cross is going to be the positive part down here, like this. Then a polar molecule is showing the dipoles. So for example, here we have water. Why not? So each bond has a dipole moment pointing towards the oxygen, which is delta negative, and hydrogen, which is delta positive, is where the cross goes. So both hydrogens are delta positive. And then we have here the dipole moment points towards the oxygen. So then the overall molecular dipole moment points from between the two oxygen-hydrogen bonds through the oxygen to the top. And so, of course, we also have the lone pairs. An ion could be an anion, could be a cation. A water molecule, we just drew that. There's the oxygen. A cation. An anion. And a cation in water. Cation in water, something like this. So the water, because it's positively charged, the water will orientate itself so that the negative part of the dipole moment is pointing towards the positively charged cation, like so. And so it'll fill all of the available space that can be filled before sort of it runs out of space. So you're probably getting about 5 to 6, depending on the size, 5 to 6 water molecules. The larger the cation is, the more water molecules that can be fit around it. Kind of like this. Okay. So here is a summary of the different intermolecular forces that can occur. So we have 4 intermolecular forces. They are called ion-dipole interactions. So that's between like an ion. So it's like, for example, our cation on the previous page, and then a dipole moment, such as a molecule with a polar molecule, such as water or acetonitrile or ethanol or something like that. Dipole-dipole interactions are, as it says, interactions between 2 molecules with permanent dipoles. So that could be something like HF, or it could be something like, I don't know, HCl. HCl. This is a dot, 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 not actually a real bond. The London dispersion forces, these occur between all molecules. They're typically very weak, and they get stronger as there are more electrons in the atom or molecule or particle. That's because they're dependent on sort of the transient or temporary changes in the electron collider around a molecule to kind of create these localized areas of positive and negative charge, which kind of create these temporary dipole moments, which help to associate the molecule and help to sort of reduce its boiling point and sort of help it glue together. Basically, these intermolecular forces are kind of a glue that sticks everything together. And then the kinetic energy is a kind of thing that breaks that bond. And then hydrogen bonds, these are the last ones. These are quite unique. They're not so universal, but they are moderate in strength. They are quite strong. I mean, compared to a bond, like a hydrogen-hydrogen bond, a covalent bond is 432 kilojoules per mole. These are like a tenth of that, but they're still significant enough to affect the physical properties of our system. So these hydrogen bonds occur between molecules with OH, NH, and FH bonds. The London dispersion forces occur between all molecules. Strength depends on size and polarizability. Dipole-dipole interactions occur between polar molecules, and ion-dipole interactions occur between ions and polar solvents. So here we're going to have a look at a covalently bonded molecule. We're going to discuss the differences between the single bonds, the double bonds, and the triple bonds. So see if you can identify the single bonds, triple bonds, and double bonds, and think for yourself which one is going to be the strongest bond and which one is going to be the weakest bond. And then let's see if maybe you were correct, even if it's just a case of putting single, double, and triple bond strengths in order. But we kind of encountered this in chapter 9 towards the end, whenever we were counting molecular orbital theory, and we discussed some of like the double bonds, the triple bonds, and the single bonds seen in like dinitrogen, in dioxygen, in difluorine, and so on. So yeah, pause the video, take your time to think about this, and then we'll go over it. Pause the video if you need more time. So what we would normally expect is that the triple bonds would be the strongest bonds in our molecule, then the double bonds would be the next strongest, and the weakest would be our single bonds. And then within the single bonds, it would be a little bit harder to know. We'd probably have to look at some tables of data or something along those lines. So here we have a carbon-hydrogen bond, 413, carbon-carbon bond, 346 kilojoules per mole. So the carbon-carbon is weaker than the carbon-hydrogen, but you can see the carbon-carbon double bond is much stronger than the carbon-carbon single bond. And then the carbon-nitrogen triple bond is the strongest of all. Covalent bonding forces for comparison of magnitude. So in a covalent bond, we typically have a strong bond. It's usually, like here you can see it's 432 kilojoules per mole for the dissociation energy of this hydrogen-chlorine bond. But then the dipole-dipole interaction strength is only 20 to 30 kilojoules, so that's less than 10% of this dissociation energy. So this interaction is very weak compared to something like a covalent bond. So intermolecular forces are much weaker than the bonds that make up the compounds. So there are 4 types of intermolecular forces that we saw before. So in neutral atoms, there's only certain types which can be applied. So in neutral atoms, molecules can have London dispersion forces. They can have dipole-dipole interactions. They can have dipole-induced dipole. So that's the force that I was talking about earlier, wherein if there is a large enough, a diffuse enough electron cloud around a particle, then what can happen is that local dipoles can kind of like create a temporary dipole. So like, for example, say we have this large electron cloud around an atom. If I were to bring a dipole moment into its vicinity, what would happen is that the electrons in this sort of left-hand side would get pushed away, repelled by the negative part of the dipole moment here. And so what would happen is we would have something like this. We've got the dipole moment here, and then we would see that we would have kind of a more of an electron density on this side and then less on that side. So this would be somewhat positive on this side because of the negative part here, and somewhat negative on that side. And that would be a temporary dipole. And of course, this induced dipole, as it's called, would have an effect on other nearby polarizable molecules, those that are large and have a large electron cloud. Those could also be temporarily polarized. They could have positive and negative regions, and that can extend through much of the molecule. And so that can lead to an increase in boiling temperatures. It can
change many physical properties in the liquid or in the system. And then the last one that's applicable for neutral atoms is hydrogen bonding. So water is, of course, neutral, and it can perform hydrogen bonding. And collectively, all of these are called van der Waals forces because he's the one that sort of discovered them or put them all down in words and categorized them for us. Ion-ion forces are slightly different. So these are based on formal charges. So we've already talked about Coulomb's law and how charged particles are defined by it. Where here we have F is equal to K times Q plus times Q minus over R squared, where the force is equal to K, which is a constant for the system, times Q plus, which is the charge on the cation, times Q minus, which is the charge on the anion. So for example, in sodium chloride, sodium is +1, so that'd be +1. Chloride is -1, so it'll be -1. And then R squared is the distance between the two ions. So here, the greater the charge, the stronger the interaction, the greater the distance, the weaker the interaction. So why is this? Well, I mean, if we have an R value which gets larger, then the denominator here gets larger. And if the numerator stays the same, then the fraction becomes larger, or becomes smaller. So for example, if the product of the top part is 1, and then we have R squared here, if we have an R value of 2, so that will be 2 squared, so that will be 1/4, whereas, so that's equal to 1/4. But if the R value then was, for example, 1/4, or so 4 squared, so that would be an R value of 4, that would equal 1/16. So this 1/16 will result in a much weaker interaction, because remember that this is times the constant gives us the force. And so the larger the distance, this smaller the fraction, meaning the smaller the force. And so there are strong forces that lead to salts with high melting temperatures. So here, water is not a salt. It has a melting point of 100 degrees Celsius. Sodium chloride has a melting temperature of 800 degrees Celsius. But magnesium oxide, where this is +2 and this is -2, has a melting point of 2,800 degrees Celsius. And you can see that's really, really high. So attractions between ions and permanent dipoles. So water has a permanent dipole. So we talked about this actually earlier whenever we were doing the concept check. So the water molecules surround the cation. So here we have the cation, say the sodium in our sodium chloride, and you can see that the negative, delta negative oxygens all point towards the positively charged cation. And then in the case of the anion, all of the delta positive oxygens or hydrogens are pointing towards the anion. And so the polar nature of water provides for the attractive forces between ions and water. Ions and molecules with permanent dipoles. So we have studied this previously, introduced solvation energy, delta H, but we haven't actually talked about this in too much detail. So this is all, like those are thermodynamics, which you'll talk about in Gen Chem 2. And so the higher the negative exothermic value, the stronger the attraction. That we did talk about briefly back in module 2, I do believe. So we have introduced this idea of solvation energy, this energy that's released whenever we dissolve something in water. You might have, well, it's not really a huge energy increase, but if you, for example, dissolve table salt in water, you might feel the glass get a little bit warmer. And that's because of this solvation energy, this energy being released whenever the salt is dissolved in the water. You might feel it, you might not. It really just depends on like how sensitive your touch is. But if you had like some way to measure the temperature, maybe an IR thermometer or something, you could probably check it out. Solvation of ions. So here we have it again. So we have the dipole moments pointing, the negative part, the oxygen pointing towards the cation that's positively charged. So negative, positive attracts negative, negative attracts positive. And then in the case of the anion, we have the positive parts, which are the delta positive hydrogens pointing towards the negatively charged anion. So when a cation exists in solution, it is surrounded by the negative dipole ends of water molecules. When an anion exists in solution, it is surrounded by the positive dipole ends of the water molecule. Enthalpies of hydration are a measure of these ion-dipole forces. So radii and enthalpies of hydration of alkali metal ions are shown here. So the lithium, so basically the smaller the ionic radius, the more energy is released. So the enthalpy of hydration is larger. So lithium, for example, has an ion radius of 78 picometers, and it has an enthalpy of hydration of minus 515 kilojoules per mole. The sodium ion has 98 picometer ion radius and an enthalpy of hydration of minus 405 kilojoules per mole. So as the size of the ion increases, the exothermicity of the process decreases. This is due to weaker ion-dipole forces. So as the ion gets larger, it becomes smaller, or so it becomes larger. The electron cloud is more diffuse. It's not as ionic in character. It becomes sort of less charged. I mean, it still has a +1 charge, but it's not as sort of just the electron, because there are more electrons now in general, it generally becomes more covalent-like than the lithium, for example. Lithium is very small, so the loss of one electron is a big difference. So there's 3 electrons. If you lose one of them, you've lost a third of your electrons, whereas cesium has a lot of electrons, probably like 60 plus. So losing one electron is like 1 out of 60, so it's really not as big of an effect. So here we have different ions, so potassium, lithium, and magnesium. Their ion molecule distance, so their interparticle distance here is d between the nuclei of the oxygen and the potassium. So that's 133 picometers for potassium and water. For lithium and water, then it's 78 picometers, and sorry, that's the R value. So the d values, as you can see, change based on the size of the ions. So increasing force of attraction, more exothermic enthalpy of hydration. So this one has a very weak force of attraction compared to the other two, and so it has a less exothermic enthalpy of hydration than it increases for lithium. And then here it's much higher for magnesium, and that's partially because the charge is much higher. And here we have them in more detail. So the strong attraction is for this magnesium water system. The sodium water system is stronger than the cesium water situation, which is a relatively weak interaction because it's just not as ionic. It is ionic, but it's still got a lot of electrons. Attraction between
permanent dipoles. So here we see what we saw earlier in that the sodium ion here has the water molecules pointing towards it. The oxygens are the ones which are closest because those are negatively charged. We have the water dipole moment, which goes sort of through here. Positive between the hydrogens, the delta positive, negative around the oxygen. Like so. So water is highly polar and can interact with positive ions to give hydrated ions in water. Molecular polarity, so we have, this is going back to also how our geometry works. So whenever we were talking about VSEPR theory, we were talking about also valence bond theory, we were talking about linear geometries, trigonal planar geometries, tetrahedral, trigonal bipyramidal, and octahedral geometries. So in the case of a linear molecular geometry, the non-polar molecule will have both atoms the same, the outer the same for a linear triatomic. So that's the case of like carbon dioxide. It's non-polar linear triatomic. Trigonal planar, so all bonding groups are the same. So for example, BF3. A non-polar molecule with tetrahedral geometry will have all bonding groups the same. So that's like CH4, methane. Trigonal bipyramidal, so all bonding groups the same, or both axial groups the same, and all 3 equatorial groups the same. So for example, PCl5 is non-polar. And then you could have some geometries such as, or if like, for example, we have PF2Cl3, if it has the geometry that I'm about to draw, then it will be non-polar.
So if we assume that phosphorus is in the middle, so maybe I'll change the color of the pen so that it's easier to see. Let's see. So if phosphorus is here, then how many chlorines, since there are 3 of them, should be on the axial groups. Here, 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 and here. And then the fluorines should be on, or sorry, the chlorine should be on the equatorial groups, and the fluorine should be on axial groups. This is also non-polar. So all bonding groups the same. So a non-polar octahedral molecule, sorry, all bonding groups are the same, or all groups trans to one another are the same. So that means the groups opposite each other. So in the case of something like this, we would have, for example, chlorine, fluorine, again, fluorine, and so the central atom could be sulfur. That's got all of the groups trans to one another are the same, so that's a non-polar molecule. Any deviations of symmetry yield a polar molecule. That's an important statement to remember. If you deviate from symmetry in any way, you're most likely going to end up with a polar molecule. Dipole-dipole forces then. So dipole-dipole forces bind molecules having permanent dipoles to one another. So here we have a molecule which has a delta negative part and a delta positive part, and it is bound together to this other molecule with a dipole moment, which also has a delta negative and a delta positive part. So you could like draw out dipole moments, and you could see how they're interacting with each other, like that. So the negative part will be attracted to the positive part of another dipole moment. So dipole-dipole forces are only present in polar molecules. So we can compare polar and non-polar molecules. So here we have propane. It's a non-polar molecule. It has a bond dipole measurement, this mu star of 0.1. So mu star is the bond dipole, which is a measure of polarity of a bond in a molecule. And we have here what appears to be that's formaldehyde, and this is methyl formaldehyde, and then we have here acetonitrile. The ethanaldehyde. So they all have similar molecular weights. There's 44, 41. Their boiling points, though, the lowest is for the non-polar, and then the highest is for these two. These two are both polar, and so as the polarity increases, so too does the boiling point, irrespective of the molecular weight. So the molecular weights are pretty similar, but they actually decrease a little bit going to acetonitrile. Here it's only 41, but yet the boiling point is still high, and that's a function of these strong dipole-dipole interactions, which glue the whole thing together and allow it to sort of deviate from these sort of what you would expect in terms of kinetic energies and whatnot. So here we again have sort of like an indication of how dipole-dipole forces can sort of affect the molecular properties of different molecules. So we have here some non-polar on the left, some polar on the right, and we're looking at their masses, we're looking at their boiling points, and we're looking at the enthalpy of vaporization. So the change in the enthalpy of vaporization. So the molecular masses here are comparable between non-polar and polar, but we look at how in each case, regardless of the mass, so for example, the mass of nitrogen is molecular nitrogen is 28. The mass of carbon monoxide is 28. So that leads to an increase in the boiling point because there are these dipole-dipole interactions. They might not be particularly strong in this case, but they are sufficient to change the boiling point. Silane here has a molecular mass of 32, similar to phosphine, which is 34, but there's a considerable difference in the non-polar and polar boiling points. And you can see that also for these other molecules down at the bottom. As the polarity for a given set of molecules with similar molar masses increases, the boiling point increases. So we have here propane, again, we have here an ether, we have here chloroform, and we have here acetonitrile. It's ethyl ethanoate. And so the molar masses are different, but what we're looking at here is the change in the order of dipole moment and how that affects the boiling point. And we can see that the dipole moment increases, so too does the boiling point. So it's around about 231 Kelvin for the dipole moment of propane, which is almost non-existent. But then as we get to ethyl ethanoate, the boiling point increases slightly. We do have a bit of a dipole moment in the bonds. In the case of chloroform, we have a reasonable dipole moment. Again, we have an increase in boiling point slightly, but we also have a decrease in molar mass. So that also contributes to the change being quite small. And then in the case of acetonitrile, we have a dipole moment D of 3.9, and then the boiling point is 355 Kelvin. And that's one of the reasons why acetonitrile is used as a, solvent in chemical synthesis. So hydrogen bonding then is a kind of special form of dipole-dipole attraction which enhances dipole-dipole attractions. And so it's because of the small size of the hydrogen this is possible. So basically what happens is we have different types of hydrogen bond where X is electronegative atoms such as nitrogen, oxygen, or fluorine. You can sort of think of it as NOF. So this is then a dash bond to a lone pair on another atom, which is generally nitrogen, oxygen, or fluorine. This is whenever X and Y are from this group NOF, then it's going to be the strongest. But other atoms with lone pairs are also capable of a little bit of hydrogen bonding. And so here, this is how we kind of draw it out. So nitrogen dash hydrogen, so that's the covalent bond. And then you can have it shared with the lone pair on the nitrogen here. This dash line indicates a hydrogen bond. So the water molecules network with one another. Each bonding in water brings about a network of interactions which explain phenomena such as capillary reaction, surface tension, why ice floats, why the molecules in a glass, like the water molecules in a glass, might curve up because of the interactions with the water. Hydrogen bonding forms when small atoms with high electronegativity and lone pairs are present. So NOF are classic examples. So it ranges between 4 and 25 kilojoules per mole, which is not insignificant. It's on a similar range with like the normal dipole interactions, but it's additive, so it improves the strength of those interactions. So for example, we can look at the trends of the group 6 elements. So we can look at, for example, H2S, which is below S is below oxygen, H2SE, that's selenium, that's below sulfur, and then tellurium, that's below selenium. And so oxygen would be the one over here, and then methane would be the one over here for the silane, for the germane, and for the stannane. We would then have, if it was linear, we would assume that methane would be around about here, and water would be around about here, but that's not the case. In fact, what happens is this. So the boiling points of the hydrides increases. So for these ones, the NOFs, they increase considerably compared to the next one down, which is a lot lower. And in the case of methane, its temperature, its boiling point is much lower than, for example, silane. So the reason why they have this order, why it doesn't go sort of like group 4, group 5, group 6, and then group 7, and why group 6 oxygen is at the top, is due to the fact of oxygen in water has 2 lone pairs. And so water is a perfect hydrogen bonder. What I mean by that, I mean that it has the same number of lone pairs as it does hydrogens, which means that it's able to form an equal number. So it's able to form 2 hydrogen bonds where it is giving the hydrogen to other water molecules, and it's able to accept 2 hydrogens from other water molecules. And so that is the reason why there is this deviation here. And it's also why the group 6 is generally a little bit higher than the rest. For example, fluorine, it has 3 lone pairs, but only 1 hydrogen, so it's a little asymmetrical. And in the case of nitrogen, it has only got 1 lone pair, but 3 hydrogens, so again, a little bit asymmetrical. Hydrogen bonding is still enough to change the boiling points, but it's not really, it's not, these are not perfect hydrogen bonders. It's the case of oxygen. So for example, this lone pair can be shared with another water molecule, like so. And then this lone pair can be shared with another water molecule. The case down here, we have an oxygen with its lone pair coming in for this hydrogen. And then for this hydrogen, we have hydrogen bonding formed. Here we have oxygen. Of course, there's also the other lone pair here and the other lone pair here. And then we have, like that. That's why it's a perfect hydrogen bond. So it can form 2 where it is the acceptor and 2 where it is the donor. So, this is the result of the hydrogen bonding. This is why we have unusually high for the first row of periodic table. So boiling points of simple hydrogen containing compounds. Notice that water has an unusually high boiling point for its molecular weight. This is the result of hydrogen bonding. So ice floats because it is less dense than water. The H bonds allow the molecules in the liquid phase to approach closer than normal for non-hydrogen bonding liquids. And this is why water has a maximum density at 4 degrees Celsius. So hydrogen bonding in H2O, ice has open lattice-like structure. So ice density is going to be less than liquid, and so its solid floats on water. So this is what ice interactions look like. They create these channels, and the density of ice is less than the density of liquid water. Density of liquid water is around about 1 or so grams per milliliter, whereas for ice it's around about 0.9 grams per milliliter. So one of the very few substances where the solid is less dense than the liquid. And so hydrogen bonding is also very important in DNA. So what happens here is that we get the pair binding, the ATGC binding. So adenine and thymine, those will pair, and then we have guanine and cytosine. So they pair and they are attracted to each other by hydrogen bonding, this special form of dipole-dipole interaction. So you can see it's really, really important. Now, of course, they can be broken apart. It's only a physical bond, but it still is a very big structure driver because it's what's holding the 2 strands of DNA together as they form their helix. And without it, there would be no DNA forming. And so, again, life as we know it would be different. So hydrogen bonding in DNA, and we can see here the black circles represent the hydrogen bond. Dipole-induced dipole interactions then, so water molecules polar molecules such as water can create or induce dipoles in molecules that do not have dipoles. So here we have water molecule coming closer to oxygen. Oxygen is a non-polar molecule and it has this even distribution of its electrons in its electron cloud. But then whenever this delta negative part of the water molecule would come into contact with the electron cloud of the oxygens, what would happen is it will distort it. It will induce a dipole moment like this, where we have now a delta positive part closest to the delta negative of the water molecule like this, which will create a temporary dipole moment in the oxygen. It's only present because the water is there. If the water was removed, there would be no longer any distortion in the electron cloud. And then this would propagate through the liquid or through the oxygen system. And so all of the oxygen molecules would eventually get an induced dipole moment. So here we have polar ethanol induces a dipole moment in non-polar iodine, and that's why iodine can dissolve a little bit in ethanol. So why is this important? So various gases such as oxygen, nitrogen, hydrogen, and carbon dioxide are not very soluble in water because they are essentially non-polar. But oxygen must be dissolved in water to sustain fish life. And this is due to the dipole or the induced dipole forces. So forces involving induced dipoles. So how can non-polar molecules such as oxygen and iodine dissolve in water? And the water dipole induces a dipole in the oxygen electron cloud, and that's how it happens. So the water here has a negative part, again, which interacts with the electron cloud of the oxygen, which distorts the electron cloud and creates this delta positive part and then the delta negative part over there. Something like this. So induced dipole forces, so the solubility of some gases in water. This data is taken from this Lang's Handbook of Chemistry, 14th edition. So that we have the solubility at 20 degrees Celsius and the molar mass in grams per mole. And so you can see that as the molar mass increases, so too does the solubility. And that's due to this idea of, there has to be an electron cloud for the water to polarize. In the case of hydrogen, there only are two, or H2 molecule, there only are two electrons. We saw that in our molecular orbital diagrams. The one electron from one hydrogen, one electron from the other, they're shared together in the sigma bonding orbital. So there's not really much of an electron. There aren't a lot of electrons in the electron cloud to actually polarize. Whereas for nitrogen and oxygen, they have a larger molar mass. They have more electrons, which can be polarized, even if it is temporarily. And so you can see that this increases the solubility. So the solubility increases as we go up in molar mass. Like so. So the degree to which electron cloud, or the degree to which an electron cloud of an atom or molecule can be distorted is measured by its polarizability. The larger the molecule, the more easily it is polarized. As the electrons in a molecule become more loosely held and more spread out, the greater the degree of polarizability in the molecule. This explains the trend that we see in solubility. So the more electrons there are, the more there are to be distorted into a temporary dipole moment, this induced dipole moment. And so the stronger this induced dipole moment, the more polar the molecule, the more it's going to dissolve in water. So that's kind of what happens. I mean, at the end of the day, we've seen for the enthalpies of solvation that like dissolves like. We'll learn a lot more about the properties of solutions in Gen Chem 2, but for now, we're just going to be happy understanding how these intermolecular forces can change and influence